Hello again, I am Iñigo Belío Apaolaza, and welcome to this third chapter of the lecture Schottky-based terahertz Heterodyne receivers. Here we are going to talk about the Schottky barrier contact itself and how to make a terahertz diode with it. Now, the Schottky contact is essentially just a metal and semiconductor contact which acts in a rectifying fashion. And this means basically that the current is allowed to flow only in one direction and it's blocked in the other direction. Another well-known example of a rectifying contact in semiconductor physics is the p-n junction, which is used a lot, for example, in light-emitting diodes or LEDs. Now, the key to understand the Schottky contact is to have a look to the energy band diagrams of the metal and the semiconductor before and after contact. So for this explanation, we're going to use an N-type semiconductor, as this is the case for terahertz Schottky contact, as we will see later. In a semiconductor, we have the valence and conduction bands separated by the energy gap, and if we have an N-type semiconductor, the Fermi level is positioned somewhere above the intrinsic Fermi level. Therefore, we have a high number of electrons that are free to move in the conduction band. An important parameter of the semiconductor is also the electron affinity, which is the energy required to go from the conduction band to the vacuum energy level. And then we find a similar concept in the metal, which is called the metal work function. And these two parameters are key in the formation of a Schottky barrier. Now, if we start bringing the metal and the semiconductor into contact, the electrons that are in a higher energy than in the metal will start to migrate to the metal until equilibrium is reached, and that means until the Fermi levels at metal and semiconductor are the same. That progressive migration of electrons causes a band bending in the semiconductor, and as a result of that, we have an energy barrier from the metal to the semiconductor side and also from the semiconductor to the metal side. The second one is typically called the built-in potential. Now, the barrier height can be calculated in an ideal case by just the metal work function and the electron affinity of the semiconductor. If we take gold and silicon as an example, we find that the barrier height is around 1.1 electron volts. Also, because of the migration of electrons, what we have in result is a region of net positive charge, and so we have an area free of moving carriers, in our case the electrons, and we call that area the depletion region. So in equilibrium, we have a barrier from the metal and the semiconductor sides, so therefore there's no current that can flow through the contact. But what happens if we apply a voltage to the contact? Well, if we have a negative voltage applied to the semiconductor side, what we have is an increase in the barrier seen from the semiconductor by that voltage. Therefore, we have a situation in which no current can flow through the contact. However, if we have the opposite case, the barrier height from the semiconductor will be reduced by that forward voltage in this case, and therefore some electrons may have enough energy to flow through the semiconductor to the metal. And as we reduce this barrier, more and more electrons will flow through the contact. And that is essentially the mechanism of a Schottky diode. What we can do now is to model that mechanism at a circuit level, and therefore we can have circuit components that model the behavior of a Schottky diode, which then we can use, for example, on a bigger circuit to see how the Schottky diode will behave in a bigger system. In a very simple equivalent circuit that we can think of, first we have the current that flows through the junction and changes with voltage, and that can be modeled just as a current source. Then, because we have a semiconductor that has limited conductivity, we will have a series resistance, but also because the depletion width changes, the length of the semiconductor that is actually conducting also changes. Therefore, that series resistance is dependent with voltage. And finally, as we have seen, in that depletion region there's a net positive charge. Therefore, we have some charge stored. Well, that's basically a capacitance. And also, that capacitance will change with voltage as we change the depletion width. So, in a simple way, as I mentioned, we can model a Schottky diode just with a current source, a capacitance, and a series resistance. Now, let's have a look to the expressions for the different components of the model, starting from the current. The mechanism that we described before for the Schottky contact can be explained or can be modeled by the thermionic emission theory, and that theory leads to these expressions, which, as you can see, the current has an exponential form. In those expressions, there are different parameters. We can quickly identify the applied voltage or the barrier height that we described before. But what I want to highlight here is that because of that exponential form, that nonlinear behavior, we can do frequency mixing of signals. And therefore, we can exploit that to build an Heterodyne receiver. That is what we are focused on this chapter. This is a representation of the resulting IV curve of the Schottky diode. And for comparison, we also have the curve for the PN diode. And as you can see, they are both very similar. Both are exponential and dominated by thermionic emission. So you may wonder, why don't we use PN diodes for terahertz detection? And the reason for this is that on a PN diode, we have the carrier transport limited by the holes, which are much lower than electrons. Whereas in a Schottky diode, this is a majority carrier device. And if we have an N-type semiconductor, electrons is the majority carrier, and therefore we have a much faster response in a Schottky diode, which is what we need to achieve a higher frequency response, therefore to build terahertz devices. The other two components of the model, so the capacitance and resistance, are going to determine what is the efficiency and the maximum frequency of operation of the Schottky diode. Therefore, if we want to reach terahertz frequencies, we want to reduce these values as much as possible. If we want to reduce the capacitance, we need to make the contact as small as possible, so we have to reduce the area of the contact. Also, what we can control is the doping of the semiconductor, so high dopings will lead to higher capacitances. On the other hand, in the resistance, the situation is opposite. So the conductivity of the semiconductor increases with doping, and therefore the resistance is reduced with higher dopings. But also, if we increase the area, we reduce the resistance. So there's a trade-off between capacitance and resistance that we need to break somehow. And we do that by this parameter here, which is the mobility of the electrons in the semiconductor. So if we have a material that has a very high mobility, we can reduce this trade-off. This is the reason why we use 3-5 semiconductor materials for terahertz Schottky diodes, because their mobility of electrons is very high. So for comparison, silicon has a typical electron mobility of around 1000 centimeters square per volt second, whereas in indium gallium arsenide, that is an order of magnitude higher, so it's 12,000 centimeters square per volt second. If we know the resistance and the capacitance of our diode, we can estimate the maximum frequency of operation by defining the cutoff frequency like this. So if we take the example of an N-type indium gallium arsenide Schottky diode with an area of around 2 micrometers square, so a very small area, that would lead to a resistance and capacitance of around 7.8 ohms and 2.4 femtofarads, respectively. And then the cutoff frequency is 8.5 terahertz, so we reached terahertz operation. We can use this diode for these means. Okay, so we have a Schottky diode that can reach terahertz operation, but now the question is, how do we use this to build an Heterodyne receiver, so to down-convert signals? And that's what we are gonna see here. For this explanation, we will assume this circuit where we have a voltage source, our Schottky diode, and then a low-pass filter with a load resistor. In this case, the voltage source is composed by two signals, the local oscillator signal and the RF signal that we want to down-convert. And here we assume these to be two simple frequency tones, so two cosine signals at the LO frequency and the RF frequency. As we have seen, the current of the Schottky diode has an exponential form, so what we are going to do is to expand the exponential term in a Taylor series and see what signals come out of it. We can write e to the x minus 1 as x plus x squared over 2 plus x cubed over 6 and so on. And that's basically the function we have in the current here for the voltage with some constants. But if we ignore the constants, we can write the diode current as the voltage plus the voltage squared over 2 plus the voltage cubed over 6 and so on. Now we substitute the expression of the applied voltage and we focus on the quadratic term. If we expand this term using trigonometric functions, we reach different terms, but the one we're interested in is this one. So we have a cosine of a frequency of the RF signal minus the frequency of the LO signal. Therefore, we have a down-converted signal, which is the same as saying that we are performing a Heterodyne detection. We also have different terms that we are not interested in, so we want to filter them, and that's the function of the low-pass filter. So this filter will reject the other components and select only the down-converted term that we are interested on. Finally, to end this chapter, we can have a look to an actual physical implementation of terahertz diodes. Nowadays, the state-of-the-art Schottky diodes use planar technology with a surface channel, such as this representation by the cross-section. And this technology basically can reduce the parasitics of the diode as much as possible, therefore reaching higher frequency of operation. Here we can see an example from Chalmers University of a Schottky diode of those characteristics. So that's a scanning electron microscopy image, and the Schottky contact area in this case is only 0.15 micrometer square. So this is an extremely small contact area. The estimated resistance and capacitance of this diode is about 23 ohms and 0.47 femtofarads, and that leads to a cutoff frequency of around 14.7 terahertz. So as we can see, the frequency of operation is very high. And with this, we conclude chapter 3 of this lecture.